All right, hello everyone. Welcome to VSPG. Today we're hearing from Professor Professor Roger Fu, talking about new surprises in the history of the geodynamo. So I'm going to introduce Roger for us. Roger Fu is enthusiastic about old rocks and optics, amongst other things. He holds a PhD in planetary sciences from MIT Earth and Planetary Sciences Department after an undergraduate degree in earth science and astrophysics, followed by a short interlude studying ethnoastronomy. Since 2017, he has headed the paleomagnetics lab at Harvard University. Roger's current research interests include the history of plate tectonics and the geodynamo on the early Earth, the role of magnetism in planet formation, and the use of new high-resolution magnetic field imaging technologies in rock magnetism, paleoclimate, and other subfields of Earth science. He recently received the sorry if I mispronounce, James B. Massel-Wayne Medal from the American Geophysics Union. Roger, we're really excited to have you today, so please go ahead and take it away.
All right, yeah. Thanks, Alex. Thanks to the organizers for giving me this chance to talk to you, share our work. So just to say up front, a lot of the stuff I'll show, as you'll see, is preliminary. We're just in the middle of working on it. So I think my hope is to just show you what we're trying to do, and then try to get some feedback and discussion going. All right. So hopefully I don't need to motivate too much why the geodynamo is interesting in this group, but just to get us on the same page. The history of the geodynamo constrains our understanding of the Earth's interior evolution. And that's because for the geodynamo to be active, there needs to be a certain heat flux coming out of the core to sustain convection. So this is, for example, a series of models that Stefan Labrosse and others have made through time. And they show, as long as you assume that the geodynamo was active, right, then there's a minimum heat flux out of the core, and therefore the ancient core must have been very hot because it must have lost a lot of heat to sustain convection. So depending on what you assume with conductivity of the core, and more recent studies tend on the higher conductivity side here. If the core dynamo was on throughout Earth history, that actually implies a very hot, deep Earth. So much so that maybe we had a basal magma ocean that lasted billions of years into Earth history. And now this entire model is contingent on the active dynamo through time. So understanding whether the dynamo was active in the ancient past is critical for this, for understanding the deep Earth's temperature structure. At the same time, getting heat out of the core involves the mantle. Right? The mantle has to be efficient at getting heat out for the core to convect. And so, for example, this is a set of models from Anar Al-Assad a couple of years ago. And she's showing that if the dynamo was on throughout Earth history, at least in this physical model that she has, you require non-zero plate velocities, i.e. some form of mobile lid plate tectonics throughout Earth history, in order to cool the core sufficiently to sustain the dynamo. Right, so the dynamo constrains the interior dynamics of the Earth. The dynamo also controls, to some extent, the loss of atmospheric species of space, especially ionized species like oxygen. The relationship is very complicated. It's non-monotonic relationship between magnetic field strength and atmospheric loss. But the point is that there is a relationship that we're starting to understand. So it's important to understand the dynamo's history, to understand that atmospheric loss and perhaps redox conditions on the early Earth as well. And finally, if you're into paleogeography reconstructions, being a paleomagnetist, I like this part of paleomagnetism very, very much. The way we track the motion of plates through time is to look at their paleolatitudes using this very simple equation. Now, this equation is simple only because we can assume a very simple geometry for the Earth's geodynamo throughout most of its history. Right? If you measure the inclination or the angle between the field and the surface, this term here, you can figure out the paleolatitude. Now, this equation breaks down if the dynamo is either not centered or off or tilted in the Earth, or if it's just not dipolar, right? It has a more complicated field geometry. Right. So in order to do any kind of reliable plate reconstructions, to understand plate tectonics in the past, you need to understand what the geodynamo geometry was. All right. So there are all these reasons to try to understand an ancient geodynamo. And we can experimentally constrain the properties of ancient dynamo using paleomagnetism. So just in very broad terms, the way that paleomagnetism is able to record any signal is that any natural rock practically contains thousands, if not millions, of ferromagnetic grains. And under certain conditions, like heating or chemical alteration with fluids, these grains can get aligned, at least statistically, with the background field. And even when that heat source or alteration is gone and the ancient magnetic field has changed, that alignment of grains persists into the modern day. And we can measure the degree of alignment and the direction of alignment of these grains in a modern sample to infer the direction and intensity of the ancient field. So with this, we can say a few things about the geodynamo specifically. We can measure its drift through time or stability. Right? Even in our lifetimes, the geodynamo has drifted, and that's perfectly normal. This is paleosecular variation. So we can look for slight changes in the angle of the magnetic field through a succession of rocks. I don't know if reversibility is a word, but it rhymes with stability, so I'm putting it here. But as everyone here knows, the Earth's dynamo reverses through time, and the frequency of that reversal is very much not constant through time. So by looking at how many reversals we see per unit time, we can understand how the dynamo is reversing, if it is reversing. And finally, this is what I'll spend most of this talk on, is paleointensity, right? So the degree of alignment of these grains that I showed in the last slide actually correlates in a simple fashion with the strength of the background field. So we can measure the intensity of the magnetization and back out the ancient field intensity. All right, so we can theoretically detect or experimentally infer all these things about ancient dynamos. What do we actually expect from a theoretical perspective? And the point of this slide is basically there's not much of consensus on what do we expect. Most people now will probably say there was no inner core on the very ancient Earth because the core was much hotter and the conductivity of the core is on the higher side of what we used to think. But what does that actually mean, right? So for the actual geometry or the strength of the dynamo. And you can find publications that basically go all the way from no dynamo, if you had a sort of incompatibles enriched basal magma ocean that actually thermally blankets the core and suppresses convection, all the way to sort of a non-modern like but existing dynamo, to a more recent paper that argues it should be basically indistinguishable from the modern dynamo. So I think this is a good opportunity to try to make ourselves useful and look at some experimental records, right? Because we really don't know what to expect. All right, so here's some records from a recent compilation. These are paleointensities translated to the equivalent dipole strength of the entire Earth. So you can see on the surface, there's a good amount of data. It goes all the way back to about 4.2 billion years ago. But what I want to get through in the next couple of slides to introduce this is that not all paleointensities are equally reliable. So I just want to talk a little bit about the sort of theory behind how you calculate a paleointensity. Right. So to calculate paleointensity, the main experiment you do in the lab is to measure the magnetization of the rock sample. And then you take that exact same rock sample and you heat it in the lab, in this, like an oven like this one, and you give it a magnetization in a known magnetic field. And then you take this ratio here. Right, so the ancient magnetic field is proportional to the ratio of the natural magnetization to the laboratory magnetization on the same sample. Now, it's important that these magnetizations are what are called TRMs, or thermal remnant magnetizations. That is a magnetization that was imparted on the rock during cooling from high temperature. So why is a TRM the only one that works, right? There's other ways to magnetize a rock, for example, during sedimentation or during chemical alteration. Well, the simple answer is just that this is the only type of magnetization we can reliably reproduce in the lab, right? You can't disaggregate a sediment and redeposit it. You can't re-alter a mineral assemblage that's already altered, but you can reheat a rock. So this is the only type of magnetization where we can construct this ratio, right, with a laboratory magnetization of the same type as the natural magnetization. So that's why this assumption is really key, right? That any rock for paleointensity needs to have a thermal remnant magnetization. And the second point that follows from this little equation here is that both the numerator and denominator here need to be applied to the same grain population, right? So the magnetic grains that carry the natural magnetization need to be the same ones that we're activating in the lab and imparting the laboratory magnetization, because otherwise this ratio would have no meaning. All right, so this is maybe the most important slide. I think it's just for any paleointensity record, we had to keep this in mind. And I think the burden of proof is on each study to show that these are valid for the samples being measured. All right, so going back to this record here then, right, and looking at some of these really old records. Some of the very oldest records here are from individual zircon grains. Some are from the Jack Hills in Australia. Some from what's called the green sandstone bed in South Africa, which is this layer here. When we worked on the Jack Hills zircons, for example, we used what's called the quantum diamond microscope. It's a high-resolution magnetic field imaging device. And what we're seeing is that when you look at the magnetic sources, so these red and blue are magnetic fields that are over the surface of the sample. This is a zircon grain. It's obviously highly, it's a fragment of a zircon grain. That's why it doesn't look like the nice sort of euhedral zircon. But the magnetic sources here correlate with these little bits of iron, right, that are sort of glommed onto the surface of this grain here. And we see this throughout the samples we looked at. So there's about 300 grains we looked at. More than 90% have either basically non-magnetic, or when they have magnetism, they're associated with the edges of these zircons. So these are detrital zircons. These are not primary igneous surfaces, right? These are abraded surfaces. So any magnetization there, right, we would conclude is not a primary igneous mineral. It's probably kind of glommed onto the grain, either during transport or after sedimentation. So that's most of the grains. So not all of the grains are like that. There are a few grains. In fact, this is another study done by Borlina et al. A few years later. Out of 4,000 grains almost 4,000 grains they dated, there are 2 grains that they found that show a clean paleomagnetic component. So this is what's called an array diagram. It's basically showing the decrease in natural magnetization and the increase in the laboratory magnetization during stepwise heating. And they actually find a nice clean component here. Well, not clean by zircon standards, I would say. So, this is one of the very, very few grains that pass all the paleomagnetic sort of quality checks. And it has zircon interior non-crack associated magnetic sources. So if anything, this is sort of the most promising grain, at least that's come through our labs. But when you look at it even more closely, it's not quite as promising, I would say. Right, when we went in at the TM scale and looked, there is magnetite there, as expected from this magnetic signal, but it's actually infilling these sort of pores, these empty pore spaces, and there's actually still some vacant pores remaining. And I think this is a really cool kind of thing we chanced on, that there's actually an empty pore space here that's got a dislocation, right? So basically a weak spot in the crystal lattice of the zircon where fluids can penetrate. And there's a little bit of iron-bearing minerals being precipitated right at that dislocation, right? So I think this is, at least I think, pretty strong textural evidence that the magnetic grains in here, while they exist and they're inside the zircon, they're still being carried in there by fluids during alteration. And if one is not happy with just the textural evidence, some collaborators actually went ahead and did atom probe tomography on a tiny piece of that exact zircon. And what they found is that you find some of these iron clusters, right? There is like, groupings of iron locally in the zircon. And one can literally count atoms of lead of different isotopes and kind of date the formation of these clusters of atoms. This is probably the worst in objective sense, like the worst geochronological result that's ever been presented on VSGP or PG, because it has like literally billion-year error bars, right? But this is literally counting atoms, right, to get a approximate age. But even billion-year error bars are good enough to show that these clusters of atoms, right, where the iron is concentrated, were mobilized and assembled relatively late in the Proterozoic, so at least 1, maybe 2 billion years after the initial formation of the zircon. So I would say, right, like if we're trying to show that the magnetization in these zircons is a thermal remnant magnetization, I would say, we might try to answer these specific questions, right? Do we see carriers, magnetic grains, that is, that cool from the Curie temperature that still exist in the sample? So all we found so far are these ferromagnetic minerals that likely, or in the case of the dated ones, I think certainly formed from later alteration. Now, you can't experimentally prove the absence of anything, right? So what if there are actually some primary minerals in there? I guess I would just say that if there are some primary magnetic minerals that are still in the zircons, they have to be dominant, right? There has to be enough of them to overwhelm this signal that we see and all these signals that we see that are secondary and not a thermal remnants. So with all this, I would say that the Western Australian zircons are not a great sample for paleointensities. Going to South Africa, maybe there is a better chance that the metamorphic grade of the rocks there and just the alteration history is a little bit milder in the Barberton Greenstone Belt. All right, so here's a panel of a bunch of South African and Western Australian zircons. Let's see if you can see the difference. Okay, right. So obviously the South African zircons are much less magnetic, and this is the same type of magnetization, i.e., this is all natural remnant magnetization, measured on the same instrument with the same color bar for the intensities of the magnetic fields. So what we found here is that basically out of the 19 Eoarchean or older zircons that we did magnetic imaging on, only one had a detectable signal, and it's a very weak one, 5 times 10 to the minus 14 meters squared. That number is probably not that meaningful in itself, but it's a very small number. It's small enough that one would really question whether it has enough magnetic grains in this zircon to actually record a background magnetic field. Right? Recall, you need a population of grains to align sort of statistically to the background field. Now, another study found from the same population of zircons many more that are much more magnetic. I don't know for sure the explanation for this discrepancy to what we're finding, but at least from the data set we're looking at, and we really wanted to find some signal here, but there just wasn't any signal here. And at least for us, I will say the zircons from South Africa are also a bit of a disappointment, because even though they're less magnetized, right, they don't have all this secondary magnetite that was delivered in there. They didn't have enough preserved primary or igneous magnetic phases either. All right, so at least in our experience, right, the zircons are not all that helpful here. So what about the whole rock record, right? So looking at whole rocks, which is what the vast majority of these data points are. So there's some whole rock records all the way back to about 3.5 billion years ago on this timeline. One of the earliest of these is the Commodity Formation, study from the early 80s. So we can take a look at this rock, right, and see whether it satisfies these assumptions that we talked about earlier. Okay, so we got a piece of the Commodity Formation here, and this is just a cross-polar optical image. And what you can see if you focus on these little dark particles here, right? So this is transmitted light, so they look dark, but they're actually what are called leucozines, right? In normal light, they actually look white, right? Which is why they're called leucozines. And what they are these relic titanium iron oxide phases that are mostly replaced by titanium oxides and titanium silicate phases, right? So in a primary, igneous basalt that it erupted yesterday, you take a thin section of it, these are going to be the main carriers of magnetization, right? Because they're full of titanium magnetite of different levels of titanium in it, but mostly they're ferromagnetic. On the other hand, these assemblages here, the leucozines, have almost no visible iron oxides, right? There are some titanium-bearing phases left. And what's more sort of tellingly, right, if you take a magnetic field image, none of the leucozines, right, are associated magnetic anomalies, right? So basically, the iron in here is all gone, right? It's just the titanium that's left, plus some silicate and oxygen that forms these relic phases. Right, so none of those are ferromagnetic, and so they do not carry any magnetic signal from the eruption of this basalt. But there is magnetic signal, right, if you look around. So what are these magnetic signals actually made out of? So you can zoom into, for example, this one here. And this, right, looking at this very high birefringence, this is actually calcite, which is obviously not an igneous phase from a basalt. So this is clearly a replacement phase, that's precipitated during alteration. And that calcite is a host to new magnetic minerals, right? So we are clearly violating this assumption that rocks was magnetized during heating, because it doesn't have any of those igneous minerals left. All right, so that's too bad. And so we really need to try harder, I would say, right, to look for Archean thermal remnant magnetization, right? So minerals that really were heated and cooled in the Archean and persist until the present day. All right, so we've gone to the Pilbara Craton in Northern Australia many times at this point, and we looked at mostly volcanics and mainly for paleo direction sort of plate motion reconstructions. But in the process of looking at all these different volcanics, what we found is, to first order, everything's altered. Everything's extremely altered, right? So this is an example from the 3.25 GA Cunaguna Arena Formation. This is what used to be a vesicle, right? Now a vesicle in basalt, in fresh basalt, is made out of air, and air is not magnetic, right? But unfortunately, we actually see quite a bit of magnetic signal in this vesicle here, right? And that's of course because it has been infilled by all sorts of secondary minerals, right? So calcite and different flavors of feldspars predominantly. So this magnetic mineral here, right, definitely is not primary, definitely not igneous. However, we can look at this mineral assemblage and gain some insights into when these minerals formed. And just looking at the alteration sequence, right, just the magnetic mineral, the non-magnetic minerals we see in this vesicle, for example, we see that it's most consistent with shallow seafloor burial and alteration by basically these convection cells of seawater in the shallow subsurface. And if you want to get more quantitative, we actually worked with some friends in Santa Barbara and dated one of these alteration phases, titanite, which is a titanium silicate. And actually has a very old age, right? It's basically indistinguishable from the emplacement age of the volcanics themselves, right? So this all suggests that these minerals are not primary, right? They're not igneous. They're not good for thermal remnant magnetization by themselves. But they are very old, right? They're as old as the rock themselves within a few million, maybe tens of millions of years. But we still don't have a thermal remnant magnetization. All right, so we looked around a lot. We drilled lots and lots of rocks, again, mainly for other purposes to reconstruct plate motions. But we spent a lot of time, 3 field seasons, or 4 now, at this region called the North Pole Dome. And it's a very thick stack of mainly mafic, ultramafic volcanics. It's thoroughly altered, just like everything else I've shown so far. But the real cool thing here, right? If you notice, there's some very well dated and still very old dikes. So maybe, right? The basalts here have been thoroughly altered, but the alteration happened early, so the magnetic particles are still old. And as long as the dikes intrude after those magnetic particles were fully formed, then the bake zone around the dike should give you a new thermal remnant magnetization, right? It would reheat the rock all the way up to the Curie temperature and back. So that's what we did, actually. We did a number of these, what are called bake contact test transits here. In this case, this is one of the kind of slightly younger, more felsic dikes in the area. And each circle here is a core that we drilled and measured in our lab. Now notice the dike is younger, but not by that much, right, compared to the country rock. But it's, you know, a good 50 million years, so it's certainly enough for shallow seafloor alteration to have happened. So if we look at the magnetization directions, right, from these samples, from close to the dike all the way to very far, what you can see is that in very close to the dike, you have this one direction I'm highlighting in red here, kind of to the upper hemisphere. And then once you get a little bit farther away, you have this other direction that's in the lower hemisphere. I'm coloring green here, that appears, but only at the very highest temperature steps. And as you go farther and farther away, the dike direction goes away completely, and you just have this country rock direction, right? And if you look at the highest temperature, so basically this point where it switches between the dike direction and the country rock direction, just that highest unblocking temperature, what you'll see is that the highest unblocking temperature of the dike direction, that's color-coded orange here, decays monotonically away from the dike contact. Right, so that's really cool because the only way to get this bake profile is through conductive heating, right, of the country rock and then progressive cooling, right? If you had a chemical alteration, for example, you wouldn't expect this gradual decline in the highest unblocking temperature, right? Because when you create new minerals, those minerals unblocking temperatures are not governed by the local heating degree. They're governed by sort of crystallographic growth processes. So I think this is a very compelling example of the rare thermal remnant magnetization in an Archean rock. Okay, so I think we have found at least a couple of places in the Pilbara that are cross-cut by these dikes that actually do satisfy this first assumption that has been quite difficult to satisfy otherwise for old rocks. Now, okay, we still got a second problem here, right? So do the same grain populations carry the natural magnetization and the laboratory magnetization? Now, if we look at this is, again, a QDM magnetic field map. This is about 2 millimeters on the x-axis here. This is natural remnant magnetization, so no heating, nothing, just flatten and polish the sample. You see, you know, a bunch of sources here. Not unexpected, there's not a lot of sources in these highly altered basalts because, again, most of the primary titanomagnetites have been dissolved. All right, so we heat this progressively, and let's see if you can see it changing. Okay, so I was trying to be funny there. So obviously it changed a lot, right? So you got all these sources that just weren't there, right, in the very beginning. So clearly you are creating new ferromagnetic sources from different reactions within the rock, maybe with the rock in the atmosphere, as you heat the rock. So that violates the second assumption now, right? Because if we heat this rock in the lab to 580 degrees Celsius, we're creating all these new grains, and whatever, in fact, we're creating about 6 times as the number of grains we started with. So whatever magnetization we impart in the lab is carried by all those grains, whereas the natural magnetization is only carried by that small fraction that was originally there, the natural population, right? So this in this denominator is heavily inflated because of that, right? And so whatever paleointensity you get will be heavily underestimated, right, by a factor of, let's say, 6, right, ish, according to this this very rough estimate. So that's not good. So what do we do about that? Right, try to avoid this problem of laboratory alteration. So we tried 2 strategies here. One is relatively straightforward, and it's basically to heat for as little as possible, right? So there's this thing called the Shaw protocol for paleointensity. It's generally not preferred if you can do heatings without alteration, but it is optimized to heat as little as you can possibly heat. And so you can try to get the sample to alter as little as possible. So maybe this is a good candidate for this sort of protocol. So here's how it works. You take the rock. Now we have to heat a first step in 0 field to, in this case, 530 degrees, sometimes 500, somewhere in that range. And that is because, again, we want to take off that low component of magnetization, right? These overprints, let's say, from younger metamorphic events. So it's unavoidable to do this one heating step before anything else. And then later on, you give this a in-field magnetization, right, at a known magnetic field, and you have to do this kind of cleaning step or demagnetization step again, right? So the result, the magnetization in a rock after this step and this step gives you the numerator and denominator of this equation. Now I skipped this step here, right? So there's this room temperature magnetization 1 and 2. So the traditional Shaw protocol, what it does is that it actually magnetizes the rock in the room temperature, so without alteration, and just checks that the magnetization, total magnetization of the grains in the rock hasn't changed, right? So this is a way to monitor whether there's alteration during these steps. So if these agree, then great. If they don't agree, well, if they don't agree by a lot, then you probably just throw the sample out. If they don't agree by a little bit, you can maybe try to correct for the amount of change in the total magnetization. Okay, so there's one issue here, right, which is that because of this overprint and the fact we had to do this one thermal step early on, this alteration check with the 2 room temperature magnetizations is not sufficient, right? It's sort of necessary but not sufficient condition for this sample being good. And that's because any alteration that happens in this very first step will be invisible to this alteration check, right? Because the first check only came in after this step. All right, so this is what we do. So this is, I guess, what we can call the sort of QDM augmented Tsunakawa-Shaw protocol, which is that we take QDM maps at all these intervals, even before the very first heating. And so what we can see when before and after this first 530-degree heating is that, unlike that case I showed you earlier, there isn't that much change in the magnetization here, right? If you look at the individual dipoles, right, the directions change. And that's expected, right? Because you are still heating the rock. A lot of these minerals are resetting. But you don't see any new minerals, at least unless you look really closely, maybe there's 1 or 2. But in general, right, every source in one rock, there's sort of a equivalent on the other side. Or sorry, in the same rock, in a different step, right? Each source in one step has equivalent on the other step. So we're not generating a lot of new minerals here, unlike in the other heating protocol. And that's expected because we're only heating once. We're heating this very quickly, only for a couple minutes. Now, once you do another QDM map, though, there is some alteration, right? There's kind of an obvious new source here. And actually what we found is this is the sulfide. The sulfides are actually being altered to magnetite, or the iron in there is being altered to magnetite, right? And this happens, as far as we can tell in our experiments, at above, let's say, 550, 560 degrees. no matter what you do. You can heat for 1 minute, you can heat the absolute minimum amount, and it's going to alter, at least in everything we've seen so far. And this is different from the really wholesale alteration of the silicates I showed you earlier, right? Which takes much longer. It takes many hours of heating to have that alteration, right? So here we basically found the mineralogical basis of this alteration, and by doing this sort of rapid heating protocol, we're mitigating or removing the effects of the silicate alteration, although we can't fully mitigate the effects of the sulfide alteration. Fortunately, of course, the sulfides are an accessory phase. There's not that much of it, right? So in the end, though, I would say this protocol is not perfect, but it's still a big step towards minimizing alteration. All right, so, oh, sorry about that. Forgot to change it in this one slide. But basically, in a few samples we looked at, there's anywhere between about 10 to 30% change in the magnetization of the rock between these two heating steps, or sorry, between these two room temperature magnetization steps. So like I said, there is still alteration, but it is not a factor of 6, right, which will be 600%. So this is a much smaller amount of alteration. And if you use that to correct the paleointensity, you get a number that's not very different from the modern day. So that's our first strategy, just to heat as little as possible, and then try to use the QDM to check as much as possible what we're altering. Strategy 2 is really half-baked right now, and so I don't have too much to say about it. But the basic idea is, well, maybe just do the normal protocol and just basically accept that we're going to alter all these minerals. And then try to use numerical processing techniques to correct for it, right? So basically, in this case, what we did here is the simplest thing. We just counted the number of sources in the initial natural map, and then after heating, right, you get a factor of 6. So very naively, one might say, the magnetization here is going to be multiplied by a factor of about 6, versus what it would have been if only the natural minerals were there. Now that's a very naive sort of first order assumption there, right? Because not every mineral grain is going to have the same capacity to carry magnetization. So what we're trying to do right now is to be more sophisticated with it. So we've been trying to develop algorithms where we actually quantify the magnetization of all these sources, right? So up to several thousand sources in the same map, and then try to actually quantify not just the change in the number of sources, but the actual excuse me, but the actual magnetization carried by these. So that's still ongoing work, but just to sort of give you a little sneak preview, if you just correct by the sort of naive 6x number I said earlier, the raw paleointensity from those experiments was only about 2 microteslas, so very order of magnitude different from this other result. But if you do this correction, you get a number that's still not quite within the margin of error, but it's certainly much closer. And we're trying to perfect sort of both of these strategies, hopefully to get sort of mutually sort of checking sets of paleointensities and see if they agree with each other. All right, so if we for now say this number up here is the most reliable number we have, right, from this sort of rapid heating protocol. All right, we can sort of we can superimpose this this here, and we can zoom in a little bit more. Actually, just so here I'm comparing not the equivalent dipole strength, but the actual field intensities. And you can see the whole rock samples we were just looking at from Australia, they're on the higher side compared to most of the zircon data that's been published. A little bit more in line with the whole rock data, right? These are those kind of gray data points. But like I said earlier, the whole rock data from the altered basalts are probably not trustworthy. But the point here is this is a little bit higher than sort of these previous estimates, which I think are problematic for the reasons I talked about. All right, so to sum all of this up, right? So we have what looks like a fairly modern-like paleointensity, right? If you look over all of Earth history here, And I didn't have time to go over this, right? But this is a paper led by Alec Brenner, who is, I think, on this call. It's coming out in Science in just the next couple of weeks, I think. But he did mostly a paleo direction sort of latitudinal motion study. But what fell out of those directions is also we observe paleosecular variation. And using that, we can try to constrain basically how non-dipolar, right, or how multipolar the ancient dynamo was. And so this is a very complicated plot, but basically the two axes are different non-dipolar components of the Earth magnetic field. And basically this dotted line here, this is the region that's compatible with the data, right? Basically compatible with the stability of the field and the symmetry of reversals we see. And this blue circle here is the kind of time of the more recent, better constrained geomagnetic field behavior. So you can see there is a lot of overlap here. Maybe this field was a little bit less dipolar, but if it was, not by a whole lot. And then very interestingly here, we actually have, at least in the time interval published in this paper, one reversal. We observe a few more over a longer time span as well. But at least in this time period, we only see one reversal, right, over a 20 million year period, right, which is really slow compared to present day. And so you can just statistically say, okay, if you had a certain reversal frequency, what is the probability that the way we're sampling, right, which is a finite number of samples, you see only one reversal. And not surprisingly, it's most likely that you only have a very slow reversal rate for you to see one reversal per 20 million years, right? And it sort of peaks out in this range of about one reversal every couple of tens of millions of years. So this one data point, like we can't exclude, right, that we just found the dynamo. We just happened to look at the dynamo in a period with few reversals. Right, we should remind ourselves that supercrons in the Phanerozoic lasts 50 million years, right? So it's entirely plausible to look at to sample the modern geodynamo in a 20 million year interval and see even no reversals. But for at least as a starting point, right, as the first observation of this, it is suggestive, I think, right, that if anything, the ancient reversal rate might have been slower than modern. Although we definitely need to look at this data over a longer time period to be sure about that. Okay, so all of that was about the very ancient dynamo here, right? So in terms of its strength, its sort of wobbliness, right, or paleosecular variation in terms of its reversal frequencies, it's pretty much indistinguishable from the modern day, maybe a little bit slower reversals. And that's surprising to me, just as a general concept that the dynamo could have gone through 3.5 billion years of Earth history without noticeable change. Given that the heat flux was certainly different back then, there might have been a basal magma ocean. The inner core almost certainly wasn't there. It's surprising to me, but that seems to be what the data says. But like I just said, maybe it's not that surprising, right? Given that there are dynamo models out there that basically give you this expectation that there was no appreciable change in geodynamo behavior. So for the last 5 minutes or so, I just want to look at the rest of this history, and obviously I can't go over it in any sort of detail. But maybe ironically, the least modern-like behavior of the dynamo actually happened much later. Maybe throughout this next 3 billion years, right, we can't just take the beginning and the end and interpolate everything in between. There's actually periods of anomalous behavior sort of in the middle. So one idea has been that maybe the dynamo progressively weakened over geologic time, or the Proterozoic, and then sort of got to a minimum state, maybe even died out, and then the inner core nucleated, and then it sort of boosted back up again, right? So the field strength sort of had this progressive decrease and then back up. So in this picture, there's a big outlier here, right? So this is the Mid-Continent Rift anorthosites from Zhang et al. A couple years ago. So is this data point reliable here? So we looked at this on the QDM again, right? So just a lot of the same procedures that we looked at earlier in those Archean rocks. Basically saw that yes, and so you have these plagioclase grains that have very well, the grains themselves are very large, but they have very fine exolved magnetites inside of them that have these nice little isolated dipoles. Right, so these are a primary igneous phase based on the geologists who study this area. That's perfectly compatible with the metamorphic history. Right, this place has been heated to maybe 100 degrees. Maybe a little more at most. Much different from the Pilbara and elsewhere in Australia and South Africa I was talking about. Right, so these look like they are primary igneous magnetizations. So that probably is, in my opinion, a reliable data point. And then if you look at a little bit younger here, right, so there is still, even if this field was high and there wasn't necessarily this progressive lowering of the field, there still does seem to be this period of very low field here, right? The field really did get pretty close to shutting down. It seemed to have gotten really strong for at least this one data point here. And then recently, Grapponi et al. Published this paper that showed there's also very low fields just a little bit after this spike. So instead of going down and back up when an intercore nucleated, there seems to be sort of this momentary spike and then another sort of settling back down to a weaker magnetic field. So same drill here. We just looked at the magnetizations here. This is actually some rocks from New Mexico, and what we found is that yes, you have the magnetic minerals in the sort of fine grain mesostasis of this rock, which is where you expect the unaltered igneous ferromagnetic grains to sit. So again, relatively pristine compared to any of the Archean samples I just showed you, and the carriers are at least capable of carrying or preserving original thermal remnants. So if we accept this data point, right, then what it looks like, and accept this data point, what it looks like, to me at least, is that there seems to have been a point where the field that got really weak, got really strong, and got really weak again. And that's not the only time this has happened, right? If you look elsewhere in the record, in just the Phanerozoic, basically, so there's quite a few other studies that corroborate that in the sort of this Ediacaran Cambrian transition time period, there was both weak paleointensities, right, very weak fields like I just showed, but also very unstable fields, right? Fields that sort of move from what must have been the paleomagnetic pole to lower latitudes and back on a time scale that, and with a frequency that's not seen in later times. Just also in the last couple of years, there have been some investigation of what has been called the mid-Paleozoic dipole low, or the Devonian dipole low. This is also a period where you get anomalously low paleointensities, even down to just a couple microteslas, right? Order of magnitude weaker than sort of average history. And then if you come even later than that, there's the very well-known and long-established what's called the Jurassic quiet zone. So this is a area on the ocean floor with Jurassic crust that you just don't see many magnetic anomalies. Now, with deep tow data, and you take a magnetometer on the ocean floor, you do see magnetic anomalies. And the reason is that simply the reversals were very quick. There were probably more than 10, maybe even 20 reversals per million years during this time period. And so when the shipborne magnetometers basically just smooth out and average over these very rapid magnetic stripes. So there are different times, even in just the last 600 million years, right, where the dynamos seem to have been either weak or unstable or both. It's not clear what caused that. I'm not going to try to explain that here, but I just want to maybe end with a slide that's maybe trying to be a little provocative here. Is that could this actually negatively impact what we thought we knew about plate motions, right? So if you look at periods of what's called true polar wander, right? So this is times where the Earth was thought to have, based on some paleomagnetic evidence, that the Earth was thought to have sort of rotated, sort of keeled over on its side around the equatorial axis. It's a little striking to me that these proposed times of true polar wander correlate pretty well with these times of anomalous dipole behavior. So maybe instead of the Earth sort of moving in this anomalous way, maybe we're actually just seeing sort of instability of the dynamo and sort of misinterpreting that as true polar wander. And I say that as someone who's signed my name, in fact, led a couple of papers that argue for true polar wander in the Jurassic just a few years ago. So, looking at this and knowing what we know now from these new papers about how robustly we can resolve these apparently weak or unstable dynamo periods in history, it does make me think twice, right, about what I thought I knew just a few years ago about true polar wander. And so maybe this is something we just need to keep a close watch on for all paleomagnetic studies going forward, right? How reliable was the geodynamo even in younger times? All right, that's my conclusion slide. So just going back mainly to the Archean things I presented. The one sentence takeaway is just that the geodynamo, even well into the Archean, is, at least to me, surprisingly modern-like in strength, its stability, and its ability to reverse. I think that's all I have. I'm happy to take questions and have discussion. Thanks.
Great. Thanks, Roger. Awesome. So there are a few questions already typed into the chat that I will ask, and I'll read aloud in a second. But you're welcome to ask your question by raising your hand. Find that raise hand button by clicking the react button, and then you can find that raise hand button. That's all at the bottom of your screen, or you can type it in the chat, and I will read those aloud. So first, Roger, we have a question from David Evans. If sulfide oxidation to magnetite is the culprit for alteration in the QDM modified Tsunakawa-Shaw method, can you mitigate that by heating in an inert atmosphere?
Yeah. Hi, Dave. Yeah. Can people still see my screen after
We can
got out
see,
of
yes.
I got out of presenter mode? Okay, great. Um, yeah. No, I will love any ideas about how to mitigate this further. So I guess two things I'll say is one that uh, Alec, who obviously is the master of these samples here. Yeah, he did try the DMAG sequence in both our ovens, which are just using air, and in the Yale ovens, which use nitrogen, right? Is that right? Or was it nitrogen or argon? But you guys use an inert
It's
atmosphere.
nitrogen. Yep.
It's nitrogen, right? So he saw the kind of alteration in the bulk samples in both cases. But I think it's still worth trying because I think what he might have been seeing is the silicate alteration, because that's by far the bigger effect, right? So I think maybe the silicate alteration is sort of immune to mitigation by inert atmosphere, but the sulfides that might be mitigated. That's something we should try. So at least for this strategy, that's something we can try. But overall, though, the inert atmosphere is not going to solve like most of this problem, it seems like.
I see Alec has just popped up on the screen with video and unmuted for a moment in case he wanted to say anything in addition to that.
Nothing substantial. Everything's been covered. Yeah.
All right. So you can go on to the next question from Zheng Gong. Zheng asks, what if the newly generated ferromagnetic minerals during heating is invisible under QDM? For example, the single domain magnetite is only tens of nanometers.
Uh, yeah. So, um, yeah, you can think of scenarios where it's not visible. All right. Basically, if you have like a kind of blanket of single domain grains that are sort of well separated. Um, I mean, I would also say, we have, we can see down to about 50 nanometers at this point in our more sensitive runs, which is, it's like sort of halfway through the single domain range. So we can't see the really small single domain grains, right? But even, the bigger single domain grains we can see. So, you could think of like a case where like you form only the really small single domain grains and they're all like very scattered. In that case, we would not see them in the QDM, so that would be unfortunate. But yeah, I think in reality, like in sort of more likely scenarios, first of all, you probably form a much larger range of grain sizes, some of which we can see. But probably more importantly, like it's probably going to be clustered, right? If you look at the alteration that we do see, right, there's specific phase changes, right, that is leading to this alteration. Right. I didn't say this here because just I didn't want to talk about this strategy too much. But yeah, like a lot of this, we did try to see like if there's any mineralogical association with these highly altered zones. And it turns out K-spar is actually a culprit. It's correlated, not 100% of the time. But my point is that because it's only like it's not like everywhere in the sample altering the same amount, right? There's like certain phases that alter a lot, and most phases don't alter at all. So my guess is that even if you do form a lot of single domain grains that we can't see individually, they'll be grouped, right? They'll be clustered in a way that we see their ensemble signal, right? Much like this, right? Like any of these dipoles is almost certainly not a single grain, right? They're all like sort of ensembles of grains. Yeah.
Okay. Our next question, Francis Westall, could you please go ahead and unmute yourself?
Okay, yes, thanks. Thanks a lot for a great talk. I want to go back to the Kamati volcanics. And what I'm going to say is perhaps will probably be corrected by Don Lowe because I know Don Lowe's online as well. I think you mentioned that you can't use those volcanics because of siderite alteration, if I understood correctly. However, that alteration was probably very early alteration. If the volcanics were erupted close to the seafloor, they would have been altered by seawater, and that would have produced some of the siderite alteration. But perhaps Don Lowe can say more about that. And if that's the case, would these samples be useful?
Yeah, no, that's a great point, and it parallels a lot of our thought process in the Pilbara rocks, right? So yeah, yeah, this probably is early, as you said. It's very encouraging to hear you sort of have that same sort of reaction to this, right? That these carbonates probably did form pretty early. Um, but the problem is, even if they're early, they still need to be a thermal remnant magnetization, right? So, and that's just because of this sort of technical limitation we have, right? It's because the only magnetization we can give the rock repeatedly in the laboratory is through heating and cooling, right? So even if the grains form early, right, in those carbonates, they're not carrying a thermal remnant magnetization. So if we heat the rock in the lab, the magnetization we see is not formed by the same process as in nature, because that happened at much lower temperatures. And so it's this ratio is going to be biased by basically the efficiency of these different efficiencies of these mechanisms. So that's why in the Pilbara rocks we try very hard to basically kind of like it's like a hack almost. It's like these rocks are highly altered, but in just a few situations they were reheated again, right? At a known age, and those are the rocks we're trying to target, right? So maybe this is a template for like if we can go back to the Barberton, we should look for places where the commodity is being cross-cut by younger dikes of known age, right? And that would be useful, I think, for paleointensities.
Thanks a lot.
Okay, great. Next, Nicholas Swanson-Heisel. Please go ahead and unmute yourself, or whoever's in the call and interested.
Hello. Thank you, Roger, for the talk. And also the whole class. Should I flip this over? I don't know if I can do that, but I don't know.
The whole class says hello. We have a lecture hall of folks.
But my question for you was regards to the correction for the magnetization, and I think you said that you applied a 10% to 33% filtering for the magnetite for the altered grains, and I was wondering if that was you looked at the specific regions of alterations, or you applied a flat percentage to the measurements that you had.
You mean this slide?
Yeah.
Yeah, so this is like what you might call like the traditional correction, right? So that's just based on the first the difference in the magnitudes of the first room temperature magnetization and the second room temperature magnetization, the first ARM and the second ARM, right? So that's been done a long time from like the I don't actually know the first paper that did it, but even before the Tsunakawa-Shaw protocol, even the earlier Shaw protocols had this step. But yeah, that's basically just looking at the total magnetization imparted, in a known bias field at room temperature, and then seeing how much it changed. And for example, if this increased by 33%, right? The inference from that argument, the Shaw protocol argument, would be that during this heating or one of these heating steps, right, there's like 33% more grains being produced. And so you should sort of divide the second magnetization here, right, this lab TRM by, I guess, 1.33, right? So basically like decrease it by 33% to simulate the magnetization you would have gotten if the alteration didn't occur. So it's a completely a bulk measurement, right? It's not coming from the QDM. What we would love to do and are trying very hard to do, I promise, is to what we'd really like to do is to use the QDM maps, right? To also get the sort of difference in magnetizations here. It's very for this especially, this is going to be very hard. It may be impossible with the QDM because the sources are so clustered. But at least for maps like this, right, we can try to quantify the amount of change, right? Just like how many new grains are we seeing? So that would be sort of doing this except with the QDM, but we're not quite there yet. It's sort of we're kind of stuck on this sort of image processing step, right? Try to automatically find all these sources and then sort of match them one-to-one, see which ones have changed. But I think it's a solvable problem. We're trying to work on that.
And thanks for providing the lecture for our paleomagnetism class today. Much appreciated.
Thank you.
I'm happy your university there's enough interest for a paleomag class. I think we wouldn't have much enrollment here.
It's always nice to see when this series can serve classes elsewhere. So that's really great to see. So David, you had David Evans, you had another mention in the chat. Did you want to speak up and start another direction for a conversation here?
It's just a comment. Thanks. That this is a really fundamental question, Roger. Your last slide of these times when we have these curious behavior of the paleogeographic and geodynamo and geophysical systems, and how they line up. And just a point that kind of we're for these times we're kind of taken back to kind of the 1950s and our understanding of maybe if the Earth's magnetic field is non-GAD, then what is it? And it comes to geological tests. And so I popped a file from Wegener's fourth edition, a few pages there where he's talking about a possible mid-Paleozoic true polar wander event that is in his mind, the evidence for this came from transgressive regressive cycles across Pangea. So might be of interest.
Yeah, no, just I'm not dumping every paleo or every TPW episode ever, right? As you know from my papers in the on the Jurassic episode, I think there is some very interesting evidence from Adria, right, of the sort of coinciding sea level changes, right? That's sort of at the same time in the same polarity as a TPW episode. So maybe that's the way out, right? Like uh, as much as I hate to say it, look at as many just kind of go away from just the paleomagnetic constraints, right? And look at these sort of non-paleomagnetic constraints.
Thank you.
Yeah, but thanks, Dave. Yeah, I've never seen this article. That's cool.
Yeah, great. Thanks. Eva Stoican, can you go ahead and unmute yourself?
Yeah, thanks. Sorry. I was wondering, so I'm a complete non-expert in this, but I was wondering, how much is Earth, I guess, typical? So would you expect that maybe the same kind of evolution would happen on other Earth-like planets as well? Or is there anything unusual about Earth that made it this way, I guess?
Yeah, I guess the hope is whatever we learn from dynamo theory, right? Like if everything I'm imagining goes as well as it can, right? Like we would have a bunch of reliable paleointensities all the way back to 3.5 going forward. And then we can test these different dynamo theories, right? And like maybe we learn that just dynamos are just not that sensitive to anything, right? To like heat flux, to the presence of a giant solid thing in the middle. And that would be I think that would be a good lesson for other planets, right? So in terms of trying to understand like what the ancient Martian dynamo could have looked like, whether Venus ever had a dynamo, that would sort of edge you towards thinking like, these planets, if they had a dynamo, maybe it was also dipolar, right, and also relatively strong, and so forth.
All right, thanks.
Yeah, I guess in terms of why the Earth is, same or different. I mean, obviously the Earth is plate tectonics, right, is sort of like the best answer to almost every question of why the Earth is different at some level. So yeah, maybe without plate tectonics, we wouldn't have had the kind of core boundary heat flux necessary for the core.
Okay.
And that's certainly something talked about on Venus, right? Because of the stagnant lid. You never had maybe a dynamo at all, but if it did, it didn't last very long.
Okay, thanks.
All right, thanks, Eva. We have a couple more minutes and no hands. Would anybody like to speak up and ask a question?
Yeah, just to announce that our next speaker will be Professor Meng from CUGB, Chinese University of Geosciences in Beijing. And we probably will have different time sort of to fit to his schedule. So probably it will be like, I think 4 or 5 p.m. likely. And he's economic geologist, but he will talk about porphyry deposits, and it's related to plate tectonics and mantle redox. So it might be relevant to people working on high temperature stuff.
Great. All right, so that's 5 p.m. Pacific time, sounds like
Yeah.
next week. Okay. All right, then with that, thanks, Roger, for a great presentation and really started a lot of good discussion.
Thank you, Roger.
Yeah,
Good
thank
job.
you guys.
Thanks.
Good work.
Thanks everyone for coming.
All right, thanks. Take care, everyone.
Thanks, Alex.
Yeah, thanks, Paul.